So here's another one of my video documentaries on a specific piece of Heathkit test equipment. And I'm going to start once again with Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to the meters chapter, I'm going to be talking about the IM-2260, which is one of Heathkit's later digital multimeters. But to give a sense of history on this, Heathkit's first digital multimeter was the IM-102. This was a 3.5 digit unit using Nixie tubes. Rather expensive. I have one of these and it only partially works. Since this was an expensive unit, Heathkit came out with a more budget priced model, the IM-1202, which only had 2.5 digits of resolution, but was considerably less expensive. Contrast $250 to $90. I have a video on this one. They soon replaced it with the IM-1212 in 1975. This one came out in 72. So in 75 they came out with the IM-1212, which was just the same circuit as the 1202, but with the parts rearranged in a horizontally oriented cabinet. Make it more of a bench piece of equipment. And within a couple of years of that, this was discontinued and replaced with the IM-1210, which was again just really the same circuit, except with the display type changed from Nixie tubes to LEDs. And that they continued to make this for a number of years, about 6 years or so. They had some more professional models which came out around the same time, such as the IM-2202 came out in 75 and they continued to make it through 81. And the rather nice 2212, which was quite pricey, but it is an auto-ranging meter. Very unusual at that time to have an auto-ranging meter. Also in the late 70s, they had the IM-2215, which was their first handheld digital multimeter. This came out only a year or two after Fluke's original 8020A handheld digital multimeter, which was the first successful model of its type by anybody. And this was obviously modeled after that. It was made to look a lot like it and have similar features and so on, but at a much lower price. I have videos on YouTube of all these models I've been discussing, if you want to look those up. Then finally in 1982, at the time they discontinued the IM-1210, the IM-2260 family came out. This consisted of the IM-2260 for about $130, the IM-2262 running up towards $200, and the IM-2264, which was around $250. All the same family, very similar specifications, but different levels of sophistication. The 2260, the subject of this video, was an LED display unit. The 2262 was very comparable except with an LCD, although it had some slight tweaks to it that made it more desirable in other ways. And then the 2264 had all the things that the 2262 did, but it also had a peak reading meter, and it had an extra button. It had an alarm function where you could monitor a signal and alarm if the signal went out of certain ranges, that type of thing. It had some other functionality, and it was the only one of any of the Heathkit digital multimeters that had true RMS for measuring AC waveforms. And of course, I already had a video on the IM-2320, which came out in '87 and was the later choice for anybody wanting a Heathkit handheld digital multimeter after the 2215. So anyway, with all that background, this video is going to be about the 2260. So the write-up in Chuck Pinson's book just says one of the 3 digital multimeters released in the summer of 1982 to replace the IM-1210 and 2212. That would be, of course, this one here and this one here. The others in the 2260 line include the 2262 and 2264, as I already said. The 2260 is the lowest price in the series. And it goes on to say, with respect to digital multimeters, the IM-2260 was the last man standing. This was the last true Heath-designed kit-type digital multimeter the company sold, and made it all the way to the bitter end. Here's the beauty shot. Alright, here's the IM-2260 disassembled, or at least case opened up. I've temporarily detached the mounting for the analog to digital and display board. This is the actual LED display board. It just has the 4 LED display modules on it. One of them is only a plus and minus and number 1, and the others are the full 7 segment types. There's nothing else on that board. And then on the A to D board, the only things that are on there are the Intersil ICL 7107 monolithic analog to digital converter and display driver IC. That's a very ubiquitous part. It's the LED driver version of the ICL 7106, which is intended to drive LCD displays. I think the 7106 is the slightly earlier chip, being a slightly modified version of the original Fluke 4290-100 chip that Intersil designed in collaboration with Fluke. So I'm gathering that they came out with the 7107 slightly after they had success with the 7106, but I'm not sure of the timeline. Anyway, that's what that is. And then there are some support components. There are couple of capacitors here and there. These are, you've got that, was it Mylar, mica, whatever it is, brown capacitor there. And these 5 ones in the white cases. And those are all the ones that are just needed for the operation of the IC. They act as part of the RC oscillator circuit. They act as the auto zero storage capacitor, the integrating capacitor for the A to D functionality, and so on. And then there are a couple of small electrolytics which I think are in the power supply circuit. There's also a pair of lamp test terminals there, which if you short them together, it's supposed to light up the all the segments on the LEDs. So this has the main ribbon cable, which provides most of the communication, and then there's the secondary ribbon cable, which I think is mostly for power. And then there's the shielded cable, which provides the actual input signal that the A to D converter is going to be converting. On some circuits using the 7106 or 7107, they're using dynamic signal balancing or ratiometric operation of the IC, because these ICs have two differential analog inputs. One of them is the reference voltage and the other is the input voltage, and by using one or the other of those as your input signal and the other one as a reference, you can get all sorts of interesting operations, such as if you were using it in an ohms mode or a resistance measuring mode, you could have a single constant current going through a fixed known resistor value and also the resistor under test, and then the voltage dropped across the reference resistor could be fed into the reference input, or the differential input of the IC, while the voltage dropped across the resistor under test would be measured by the normal input circuit, and thereby taking a ratiometric measurement of those two resistors and figuring out the value of the unknown resistor by the comparison. And if you flip those around, then you could use it to measure conductance, for example. In this Heathkit circuit, it's a little simpler than that. The reference input is just held to one of a couple of different fixed reference voltages, and all of the signals for measurement are being fed dynamically into the regular differential input. Okay, so much for that. Here you have all of the switches for functions here and ranges there. The pins on the switches go through into the circuit board and make some connections, and then additional connections are made on the top by direct point-to-point wiring, jumpers, and ribbon cables coming off. Note the cutout in the case there. The same front panel and brackets here were used through the entire series of meters to which the IM-2260 belongs. The IM-2262 is the LED display version of this meter, although it's not an exact clone as one might imagine, with only the IC being the LCD version and an LCD display. The circuit is subtly different in other ways. I'll get to that in my video on that meter. And then the 2264, which is sort of the queen of the series, appears to just be the LCD version with an added peak detecting meter, which would be mounted behind that cutout. And again, that's a simplistic view of what's actually happening with that, and I'll do a video on that machine as well. But for this 2260, this is the, one might say, the lower end, the base model of the series. But it's also the longest lived one. It's the first one Heathkit released, and it's the last one they continued to sell after discontinuing the LCD versions. They sold this one right up until they went out of the kit making business. Anyway, so back into this here. Already covered that. There are a couple of op amps. One of those is going to be for the AC converter or precision rectifier circuit. And I haven't studied the schematic yet, so I don't remember what the other one's for. There's a 4016 down there. That's a CMOS logic chip, and I'll have to investigate and see what that's doing. This is the AC calibrate trim potentiometer there, which suggests that this is the op amp used in the AC converter because they're so close to each other. The 4016 is a analog switch. It just popped into my head that, yeah, the 4016 is a quad analog switch. So it acts like 4 discrete switches, each of them digitally controlled, and that's used somewhere in the circuit to switch some signals around. and I think this is the 2K, so this is the basis adjustment for all of the resistance ranges, and it's far away from the other trim pots for the resistance ranges. And again, I haven't studied the schematic yet, but I'll bet when I get to it we'll find out that the 7107 is being used in a ratiometric mode for resistance measurements, and this pot here will probably be one that dictates what the reference voltage is applied to the IC, while all these other ones are going to affect the input voltage applied to the IC. So I bet that's why this is way over here. Yeah, this is the 2 volt cal here. This affects all voltage and current measurements. And this is the 0.2 volt cal. And that again probably explains why this analog switches here. We're probably going to find that there are some resistor dividers that have these 3 pots in them, and that the analog switches in here are going to pick from one or another of those and feed that into the reference input of the IC. That's my story, and I'll stick to it unless study of the schematic tells me otherwise. The meter is powered either from a pack of rechargeable batteries or rechargeable cells. NiCads is what it's intended for, but I think it might be able to work with nickel metal hydride. Again, I'll find that out. It has a label on here with all the internal reference voltages and resistances. The bank of reference precision resistors are here, and so their factory measured values are on this label here. There are a couple of posts here for the low cal and high cal, and during calibration the meter is used to measure its own internal reference voltages, and that's how you would calibrate it for AC volts. And then due to the nature of the circuit, that's also calibrating current at the same time. This is the AC cal pot down here, as I already mentioned. What else do we have? Oh yes, the circuit is probably going to be using a plus and minus or bipolar power supply in at least some parts of the circuit, and I'm going to say that it's probably something less than 9 volts, because the batteries would generate about 9 volts, and the AC power adapter is also looking for 9 volts. It's going to assume those are not regulated, so it's going to regulate that down, and we'll find out that the actual regulated voltages are probably somewhere between 6 and 7, maybe 8 volts, probably in the 6 or 7 volt range. Again, I'll verify that when I get to the schematic. But it's only a positive voltage being produced by the batteries or by the AC power supply. And this is the only inductor on the circuit board, so again, schematic study will reveal, but I'm going to guess that that's a part of the power supply circuit that isn't a normal step-down transformer. It's probably used in a small switching supply or something like that that's going to generate the negative power rail. Again, we'll get into that further. What else can I say about this here? Yeah, way over here we've got a couple of high power resistors, 3 of them, and those are likely to be part of the current shunts. And there are a couple of big beefy diodes. Those are going to be protection for something. They're kind of near the resistors. They might be used to protect the constant current source used for resistance measurements. Again, that's my best guess at this moment. And yes, the dedicated 10 amp jack is right down here, and it comes in right next to this resistor, so I think that's what we'll find these are. These are the shunts. What else do we have here? I think that's about it. So I'm going to button this up and then I'll do a demonstration. The cases for these this series of meter, and they also I think used it for a couple frequency counters. I'd have to double check, but I think they use these for one or two other things besides this set of 3 meters. Anyway, it's a pretty tough plastic case that originally comes in a top and a bottom half, and you stick them together, but they're not intended to be taken apart again. And then the handles, finally Heathkit wised up and put some handles with detents on them instead of their old scheme of just having a bent aluminum handle that acts as a handle and a kickstand, and then just putting it in with a bolt and a lock washer to hold it in position. That never worked well. These have a spring on them and you pull them out. Yeah, so once you pull them out, then it releases the detent and you can move them to another position. And there are several positions they can be in. And you can adjust the spring tension with the screw and the large washer in there. Otherwise, the case has these metal brackets in the rear which slide into slots going around 3 sides, and those provide mounting positions for the slide-in electronics chassis, and also for the battery pack and the rear panel. And you have to slide the whole thing in from the rear, I believe. Or is it from the front? No, from the front. You slide it in from the front. So we get everything lined up like this. Then the back panel and battery pack go in, and you slide those in. Reach in through the back and pull that to the rear. And then this has to go in and align with, actually it aligns with nothing. And finally it gets in to the point where it's almost all the way in there. And then it should just sort of drop in. There we go. It goes up against the plastic flanges in the front. And when you do that, then metal brackets on the back of the circuit board line up with these brackets, and you put in screws there to hold those in position. So those 2 screws are in, and that holds the whole assembly together. So the front panel is no longer loose. And then all that remains is to put in the battery pack, which also has the small circuit board for the power jack. So kind of like that. Have to make sure the wires don't get pinched. Okay, so like that. There's some instructions on the back for doing diode tests. And it takes 6 1.5 volt C cells. They're intended to be, you can put regular alkaline cells in there, or by setting up a jumper on there you can set it up to use rechargeable batteries or rechargeable cells. And it mentions that there's an internal fuse, 3 amps for the normal amps ranges. That's no good for the 10 amp range. That fuse is not used for that part of it. And there's the IM-2260 sticker and their series number. It's not a serial number. So you can have the handle around the back if you're just setting this on a bench and don't want the handle at all to be in the way. Or the handle can be rotated to the front as a carrying handle. or the handle can be a kickstand at various angles. So how to power these guys? Well, the most obvious thing is just to slap in several alkaline C cells and just run them off the batteries. But you can get quite a few hours of operation out of battery operation, and it's not too bad to just pop these 4 screws out and change the batteries. But most of these things I prefer, if they're bench mounted, I want them to run off of AC power. And Heathkit did provide that jack back in there. Now this is a smaller jack. It's unconventional by today's standards. Here it is. This is decidedly smaller than the usual 3.5 millimeter or 1/8 inch phone plug that we see today, but it's the same basic style. This is a smaller size. I make my own power packs for these things when I get them. I think there's at least 4 models of Heathkit that use the same power pack, and it's what they call the PS-2350. So I make a clone of it, and it works with at least these 4 models. The IM-2215, that's Heathkit's first digital handheld multimeter, and then the 2260, 2262, and 2264 series, of which this meter is one. They all use the same kind, and this is just a little switching power supply, generic type. It's a 9-volt output, and it's good for 0.55 amps, so a little bit over half of an amp. More than enough to power any of the meters that Heathkit made that could use this general type of power supply, the PS-2350. But the plug, again, is that sort of oddball type. I'd tried getting some ones off of Amazon, but they were all plastic and obviously made in China. Dimensions are right, but the materials are bad. You can't solder the wires even with a lot of skill without just melting everything. So I started using the Switchcraft ones. They're much better made. The housing here is machined and anodized aluminum, so it's a high quality plug. They cost a little bit more. They're, I think, pushing $5 a piece for those things. But anyway, so you just need a 9-volt regulated DC power supply. And I don't know the current requirements of all meters, but certainly the half of an amp or 550 milliamps, which is a common size, is appropriate, and these are wired for center positive. So you have to make sure the tip has the positive voltage and the sleeve has the negative side, and just wire it up. And then that just plugs in to the back here. Now, because it's so recessed, you can't hardly grab the back of the plug housing, but thanks to those knurls that Switchcraft put on there, you can just get a grip, or you could just tug on the wires really, but it's safer to get a grip on the housing, and it is enough to reach. Then I'd mentioned that this is Switchcraft model 850X. That's 850X as in X-ray. It's a very common part, not too hard to obtain. So let's turn it on. It's in ohms mode right now, so it went to infinity. Let's put it on DC volts. That's more like it. Nice clear red LED display. The front panel is a nice looking panel. Power on off switch. A note to look around the rear to see how to do the diode tests. You've got DC volts, AC volts, DC amps, AC amps, and ohms. So those are your 5 functions. And then you can pick from 1, 2, 3, 4 different ranges If you're in ohms, it's a 2K, 22 or 20K, 200K, 2000K, which is 2 megs, or 20 meg range. It gets you a fifth range there in ohms. If you're in amps, it's 20 or 2 milliamps, 20 milliamps, 200 milliamps, and 2000 milliamps, or 2 amps. That's your 2 amp range. And then in volts, you've got a 2 volt, 20 volt, 200 volt, and up to 1000 DC or 750 AC. Those are common limitations on digital voltmeters of this era. Even the fluke models, such as the 8020A, have the same exact limitations on voltage, AC and DC. Now, if you want to check the battery voltage, then if you're in voltage mode, you can kick this range in and check the battery. Since I'm in DC volts, it's just saying you should see at least 6 volts there. And I'm seeing about 9 volts. And that's because that's what's coming in from my regulated power supply. But if you had actual batteries in there, then you could monitor them, and as long as you had at least 6 volts, you're in good shape. And by the way, the batteries in here don't add up to 6 volts. They add up to 9 volts, or close to it. So it can operate down to 6 volts, but normally it'll be higher if you're operating in battery mode. Okay, so that's the switches. All features on here, all functions and ranges, except for the 10 amp range, use the same 2 jacks. That's a convenience, because all of the other meters that Heathkit had require you to be moving plugs around for at least some of the functions. Usually you have to go to a separate jack for even low milliamps ranges, but here it's all done through these 2 jacks. So it's 2 amps max, or 1000 volts DC, 250 volts AC, and a resistance are all handled with these. But if you want to go to the 10 amp range, then you have to move your red lead down to the white plug and use those 2. So let's do a demo. Okay, I'm in the DC volts function, and I'm in the 2 volt range. I'm connected up to a DC power supply, and I'm going to give it about 1 volt. I checked this earlier by having another professional voltmeter tied in, and this was dead nuts on. It was just a hair less than 1 volt. So this is accurate. I can go up to 3 volts and it overranges. So I have to go up to the 20 volt range. And we've got just a hair under 3 volts. That should be 9 volts. That should be 14, 18. That's 22 and it overranged. So I go to the 200 volt range. I've got 22 right on, 28, 32, that's the maximum my power supply will put out on DC volts. So the DC volt range is working fine. I'm going to back this down to 24 volts. Okay, I've got it on the AC volts function, and I'm in the 200 volt range. And I've got the meter hooked up to my variac. I'm going to just crank her up to approximately 50 volts. And sure enough, 50 volts, almost 50.1 or 51. There we go, it's hovering right on it. There is a capacitive lag on this meter. The impedances are fairly high, and then they have a capacitor across the inputs to the A to D converter that takes a moment to charge, and so it takes a little while for the readings to stabilize after you make an input change. Let's go and crank it up to about 100 volts. Doing good. I'll crank it back down. Okay. It's working on AC volts. Now the way this meter and pretty much all digital multimeters work is that you've got the input scaling function for volts, and then if you have AC volts, it taps off the output of the scaling, runs it through the AC converter, which turns the AC to DC, and then runs that into the analog to digital converter. If you don't have it in a DC or an AC range rather, then the input signal after the scaling bypasses the AC converter and goes directly into the A to D converter. So if I know it's working on DC volts and it's working on AC volts, then all I have to do is test it on DC amps, and I don't really need to check it on AC amps because unless there's a problem with the switching, all the other components and circuits have already been tested in the other three functions. So I'm going to go to DC amps now. Okay, I'm in DC amps. I'm going to put it in the 20 milliamp position because I'm going to be using a 4 to 20 milliamp loop tester to manipulate the DC amps. I use this on all of my demonstrations. It's just a good way to do a quick evaluation of the amps without having to rig something else up. I've got a power supply to provide loop power for the 4 to 20 amp loop, or 4 to 20 milliamp loop I should have said. I'm going to turn it on now. I get my loop OK LED, and it's reading just about 12 milliamps. This has the knob set to the 50% position, 50% of a 4 to 20 milliamp span, which is 16 milliamps. Half of that is 12 milliamps. So 12 milliamps is where I should be. Now if I move the switch up here, that'll put it to the 0% position, which is 4 milliamps. We're just right there. This is actually more to do with the calibration of this. It needs to be touched up. Go back to 12 milliamps, turn the other switch on. That's going to take it to 100% or 20 milliamps. And it's reading a little bit low, again, because this is slightly out of cal. But we're basically up there. Take it back to the knob, and now I can change the knob around. Ta-da! So DC amps are working, and we know AC amps will work as well because we've already checked all the other sub-circuits that would be involved. Okay, checking out resistance mode. I'm going to put it in the ohms mode. I'm going to start low with the 2K range, and it's reading infinity now because my decade resistance box is not selected to anything. If I pull this out and then short the leads, it goes down to nearly 0 ohms. The only thing we have is a little bit of quiescent resistance in the test leads that it's showing there. So open circuit, it shows infinity. That's how the A to D converter shows over range or infinity. So let's crank her up to let's take it up to 5 ohms. And it's reading just a hair high, 0.006K. If I go up to 8, you know, it's still in the ballpark, but we have that quiescent resistance that's throwing us off slightly. Let's go up to 20 ohms, and it's reading 22, So again, we have to subtract a couple ohms due to the quiescent resistor leads and extra resistance inside the box here. Let's go up to 70 ohms. It's pretty good. Let's go to 400 ohms, showing 0.4K and just a little bit. It's still showing that 2 ohms quiescent resistance, so that's remaining pretty constant. Let's bring up 1K here, and now we have 1.4K. 1K plus 400 ohms, 1.4K. And let's go up to 5K. It overranges, so I go to the 20K range, and it's showing 5.4, which is what it should be, and some residual stuff down there. Let's bring it up to 20K. We've overranged. Go to the 200K range. It's reading 25.6, 25.6, 25.4. So again, down the low end we've got a little bit of residual stuff going on, but it's really close. And I'm not sure that the precision on this is all that great, so I tend to believe this. Actually, let's do a quick sanity check. So let's just use this Fluke handheld up here. So for 25.4K, 25.46, let it stabilize. So it's reading a couple of points high on the least significant digit. That's more likely due to the test leads and things, but it's also the calibration on here. When I obtained this, it didn't work on the ohms mode at all. And when I did the troubleshooting, I realized that whoever had this last, or whoever had worked on it last, had probably tried to calibrate the ohms range and did it without using the manual probably. So they were trying to adjust the trim pots for the various ohms ranges without first calibrating the reference voltage trim pot. Once I calibrated it according to the proper Heathkit procedure, then I was able to satisfactorily adjust the ohms range trim pots. But they're very touchy, and it's really hard to get the least significant digit to stay in, so that's accounting for most of that. So let's just go up a little bit higher here. Let's go up to 700K. So obviously it overranged. I have to go to the 2000K or 2 meg range. So it's reading 728 thereabouts. 725, yeah. It's bouncing around a little bit, but it does drift into the 725 that I have here. It gets there, but there's a little noise on it. It's not completely stable, but it's basically working quite well. Of course, I can go to the 2 or 20 meg range, and it's still going to read the most significant digits of 0.72, which is 72 here. It's just putting it way into the high megs range. So that's working well. And we're back to virtually zero. Unless I go to the lowest range, and then it's still showing that quiescent resistance. So ohms range is working well. According to the manual, and the diagram on the back of the meter, I can check diodes with this. To check diode forward resistance, it's necessary to put it in both the ohms mode and the DC volts mode at the same time. and the switch interlocking does allow that and put it in the 2K range. Connected up forward biased, and it's showing me the forward voltage drop of the diode, so 0.58. You normally expect about 0.6 volts for a silicon diode. So that seems to be working. And I should mention that that test that we just did is putting 1 milliamp through the diode, and the forward voltage on silicon diodes can vary a little bit depending on the current through them. So if we were putting more current through this, we may have a different voltage drop. But it does say right on the back that they're doing the test at 1 milliamp, and so a 0.6 volt reading is typical for a silicon diode. Now to read reverse, we have to connect the diode in reverse, obviously. We just do this in ohms mode and in the 20 meg range. And this is checking leakage in the reverse direction, and it should be very high, or infinity, I think. So the 20 meg range. Yeah, so I have it connected and it's still showing infinity. It's this diode's in good shape. It's not leaking. It's acting as a diode should. Alright, so the demo of the meter is complete, and I'm going to go and talk about the schematic diagram now. Alright, let's look at the circuit for the IM-2260. This is a long, stretched out schematic. It's drawn better than some of them around this time. It's still apparently hand drawn to some extent. Not to say it's freehand, it's just it doesn't look like it's CAD drawn. Because of the layout, I'm going to once again resort to my usual sketches of each circuit block. I'm not going to go into great detail on the operation of the main IC, in this case the ICL 7107, which is an intersil part, still being manufactured by Maxim today, and maybe some other chip makers. It's become kind of a generic part. So if you want to see a more detailed breakdown on the 7107, 2 or 3 other videos I've done recently on Heathkit digital multimeters have a much more detailed breakdown on the 7106, which is the LCD display version. The same in most details, and those are the things I'm going to skip. But just to give a quick refresher, the 7107 is a monolithic dual slope analog to digital converter with extra features such as auto zero and a built-in current controlled LED drive circuit, which does not use multiplexing. It drives all digits at the same time. There is a built-in oscillator which relies on an RC sub-circuit external to the chip to select the clock frequency. It can be driven using a crystal. Even though it doesn't show it here, it is possible to just use 2 of the pins and put a crystal on there. It's also possible to drive from an external clock into, I think, just pin 40. But it's common to do it this way. The frequency is not actually critical. If the frequency drifts a little bit, it does not affect accuracy. It still has a test pin, although it works slightly differently on the 7107 from how it works on the 7106, just because of the display type being a bit different. It still has a differential input, ref high, ref low. It measures the voltage between those 2 pins as a reference voltage. It has the main input, also a differential input called in high and in low. Differentially measures the voltage across those 2. And then internally it takes the ratio of this differentially measured voltage and this differentially measured voltage. And then the ratio is multiplied by 1,000, and that number is what gets put on the display. There's a reference capacitor that hangs out here. It's just another one of those things that they can't do inside the chip, or which needs to be a different size or value depending on how the designer's using the chip. There's the circuit common, which is both a possible ground reference depending on how the chip is being used in the circuit. It's also an output reference voltage, which can be used in various different ways. Then you've got the auto zero storage capacitor here, a buffer resistor, and an integration capacitor. This is where the dual slope integration happens using this capacitor, and they're all tied together here. Now, one thing that's a little different in this instance, usually this is a single resistor here, but in this instance they've used a 470K and a 47K, and the 470K is shorted out by an electronic switch. And for those viewers who've seen my breakdown on the Fluke 8020A handheld digital multimeter, which uses the Fluke proprietary 429100 analog to digital chip, which was the forerunner of the 7107 and 7106, and very similar in almost all ways. I mentioned that it had a limited auto-ranging type of functionality, which the intersil versions, in other words the 7106 and 7107, don't have. In this design, Heathkit has chosen to implement a sort of similar functionality by messing with the integration circuit by way of changing the resistor value here. You either have the combination of the 470K and the 47K, or you just have the 47K if this one's shorted out. And that changes the operation by an order of magnitude here. So it effectively is a range switch. And they're calling that the 0.2 volt and the 2 volt range. So depending on how other circuitry operates two key signals, the 0.2 volt signal and the 2 volt signal, the whole circuit operates as if it was a 2 volt sensitivity or a 0.2 volt sensitivity. And that simplifies some other things in the circuit. Let's see. VSS, that's the minus side of the power supply, and it's supplied from a voltage divider coming off a minus 6 volt power supply. Heathkit perversely likes to show these things pointing up even if they're negative. I always figured if it was negative it should be down and then ground should be up, but it's a drafting preference. Then the rest of the chip is all just the driver pins going out to the 3.5 digit LED display. Otherwise on here we have some switching that does double duty. Part of it handles just driving the decimal points, which the A to D chip does not know where they should go because it doesn't know what kind of input scaling is being used over here. Therefore that has to be done more manually through a combination of function and range switches and a little bit of diode logic. But these switches also do double duty, as I mentioned before, in determining things like if the display should be blanked in certain modes, and it also factors into the range selection, as I mentioned, the 0.2 and the 2 volt. This signal here, for example, that's derived from part of this, comes through these two additional switches, and it comes over to the circuit that generates the 0.2 volt and the 2 volt control signals, and I'll talk about that more. There's the power supply circuit. Another regulator circuit for the LEDs. The reference resistor bank, which is used for calibration, And also over here is a reference voltage divider in the power supply circuit that provides 0.19 volt and a 1.9 volt negative voltages, but those are reasonably precise values derived from the power supply that are used for calibrating the rest of the meter circuit. And then up here we have all the front end range and function selection switching and the appropriate resistor dividers, current shunts, precision constant current source for the ohms range, and the AC converter that converts AC signals to DC whenever you're in an AC range. So with that overview, let's go into the details. Alright, the power supply circuit for the IM-2260. So it all starts with the optional AC power adapter, which provides roughly 9 volt DC. It's not regulated necessarily. It doesn't need to be. And the Heathkit supplied AC converter or wall wart was not regulated. Although, as I've mentioned elsewhere in this video, to power this meter and the other ones in the series, I've created my own clone of the Heathkit power supplies, but on mine it's regulated 9 volts. Doesn't change anything over here. You also have a bank of 6 C cells that are nominally alkaline but can be NiCads. And there's a jumper on the circuit board that determines if you're using regular, in other words, something besides rechargeable batteries, or if you're using NiCads. There's no provision for any other battery technology that's rechargeable other than NiCads. So if you don't have anything plugged in here, then the internal switch on the power jack just couples the battery's plus side, or the minus side of the battery is connected to circuit ground. The plus side comes through the jack switch and then through the power switch and then on into the rest of the power supply circuit. If you do have a power converter plugged in or a power adapter, then this switch opens up and there's no longer a connection between here and here. So if you just have your power source plugged in here, then that power goes through here, through the power switch, and into the rest of the power supply circuit. But if the power switch is turned off and you're plugged in over here, then that voltage is applied this way through a 6.8 ohm 1 watt resistor, and assuming you have the jumper here in the NiCad position and you have installed NiCad cells, then that charges the battery through this route. If you do have the power switch turned on and you've got this, in addition to the power supply powering this circuit, it also provides a trickle current through this larger resistor. It's 100 ohms instead of 6.8 ohms, and a diode, and it allows a slower charge to be happening while you're powering the meter off of the AC power adapter. So that's what's going on there. And again, if you have the jumper set to regular, then neither of these do anything and there's no charging activity of the battery. So the rest of the power supply circuitry has several jobs. It has to provide a voltage tap for the battery voltage checking function. It has to provide a plus 6 volt power supply rail. It has to provide a negative 6 volt power supply rail. And it has to provide a plus 11 volt power supply rail. And there's actually a 4 volt rail as well, which I don't have shown here. But those are the main things. It also has to provide some fairly precise voltages, like I already mentioned, a negative 0.19 volt and a negative 1.9 volt. The test points for those, so that you can use that for meter self-calibration or standalone calibration. So it's pretty easy to figure out how the battery supply is worked out. Oh, I lied. The plus 4 volt circuit is shown here. I thought I'd put it on another drawing. So the incoming power from the power switch is filtered by this capacitor. I'm just calling this point plus power. Then it goes over here, and through a 1K resistor it becomes the battery tap. So assuming that you're running off the battery, this voltage will change depending on how healthy the batteries are and how much charge they have in them. And that's used for the battery test function in the meter. There's also this little circuit here, which is just a series regulator, a linear regulator. There's a plus 6 volts regulated rail, which I'll get to, and that's used on the top side of a voltage divider, which provides 5.23 volts in the middle, and then that's used to drive the first transistor in a Darlington pair, which drives the second transistor in the Darlington pair. And this conducts as required to achieve a plus 4 volt output, but there's no feedback on this. In this type of configuration, if you supply 5.23 volts here, you drop 0.6 volts for the base to emitter junction here, another 0.6 volts for the base to emitter junction here. The voltage here will be the 5.23 volts minus 0.6 minus 0.6, and that does turn out to be 4 volts. And again, there's a little filter cap there, so it's a very simple linear power supply, which isn't regulated because it has no feedback, but at least it is controlled based on a reference voltage. It's not just flapping around in the breeze. The rest of the voltages are derived from a sort of kind of switching power supply, a fairly basic circuit, and it consists of a switching transistor that dumps power from the plus power rail into the primary of a small transformer, the other side of which is its circuit ground. Then the secondary has feedback from part of the coil back through this transistor, which then controls this transistor, and the whole thing operates such as to try to regulate the output voltage, and I'll talk more about how that happens. The full secondary voltage is applied through this diode and becomes the plus 6 volt power rail, which again should be held fairly tightly, but the circuit does not monitor that directly. What it does is it just uses this tap here back through this transistor, which is kind of working like a comparator and kind of differently, and then that again affects how and when and for how long this transistor is turned on, and thereby changes how much energy is dumped into the primary. And then with the load, which should be fairly constant from all the circuitry out here, you end up with a voltage that stays pretty close to 6 volts. There's also this cute little circuit here. It's kind of a voltage doubler circuit, and it results in roughly twice this voltage, so it's a nominally positive 11 volt power rail, and I'll go into a little more detail on that. Also not off of here, but off of this point, off the primary of the transformer, is a diode facing the other direction, and along with its filter capacitor, this provides the minus 6 volt power supply. And this does have some feedback. It taps off of the actual point here, and is applied to the anode of a 6.8 volt Zener diode, while the cathode of that is tied to the plus power rail through this resistor, and there's a filter capacitor here. And that's what controls the base. Well, whether this transistor conducts or not depends on whether you have at least a base voltage of 0.6 volts higher than the emitter voltage. So the base is being driven off of this feedback from the actual -6 volt power rail, while the emitter is being tied to this tap here. So depending on what voltage is being tapped off here, it's being compared to the voltage here, and depending on which one's greater and how much one's greater than the other, it determines whether this transistor turns on or not, and how much it turns on. And the timing of when it turns on is in sync with the oscillation that goes on here. If this transistor turns on, then it pulls the base of this PNP transistor low, relatively near ground through this path, and then that causes it to turn on and dump energy from the plus power supply up here into the primary. So once this reacts, it's going to raise the emitter voltage, which will make it greater than the base voltage, and it'll stop conducting, which will turn this off and cause it to stop dumping power, at which point the emitter voltage becomes lower compared to the base. This turns back on, which turns this one on, and it dumps power, and it cycles in an oscillation. So that's your basic oscillation. The timing of that is what determines the actual regulation, the output voltages. And so what you've got here, if you are actually at -6.2 volts on this rail, that same voltage is here on the anode of the Zener, and if you add the Zener voltage to the -6.2 volts, you end up with 0.6 volts. That's the difference between these two voltages. You end up with 0.6 volts here, which we know is the voltage, the typical voltage of the base to emitter junction bias voltage. So in other words, it's right on the cusp of conducting, depending on whether this voltage is higher or lower, for example, as I already mentioned. So the oscillation occurs because of this, but the actual voltage derived here in comparison to this determines how much this turns on and how much energy is put through, and thereby, with the relatively constant load out here, how much voltage is produced. Here's the reference voltage circuit. You've got your -6.2 power rail, you've got ground up here, and that works out to a 4.36 volt drop across this resistor, 1.65 volt drop across this resistor, and there's also a drop here of 0.184 volts. So you end up with a negative 0.184 volts, which Heathkit just simplifies and calls a minus 0.19 volt. And of course, this is a theoretical value. In reality, it might as well be this value. And then if you add the 1.65 volts to that, you end up with the minus 1.83 volts, or Heathkit calls it the minus 1.9 volt reference voltage. Now I promised to spend a little more time on this little voltage doubler circuit here. And what I've tried to do is treat it as if there's, I actually call it a positive half wave and a negative half wave. That's not precisely true, but for this discussion it'll suffice, I think. On one part of the cycle of the oscillation that's going here, this diode here will be forward biased. That's this diode up here. This is just redrawing the part of the circuit that's actually conducting at that moment. So energy is dumped into this 47 microfarad capacitor, charging it up, and then through this diode it's applied to this 4.7 microfarad capacitor, the negative side of which is connected out to the load and also to this capacitor. And as I wrote here, use the rectified transformer output to charge C117 via the series C118. I think it has to be doing that in order for this to work. Of course, when you apply a transient voltage to the capacitor, if it's in series, acts more or less like a short circuit, or at least a fairly low impedance. So this is almost more like a resistor for that brief moment in the oscillation. So it does charge this capacitor up and then charges this capacitor up, and it's charged up to the same voltage as this, so roughly 6 volts. This is the 11 volt output here, but in order to get 11 volts, something else has to be done. So on the other half of the oscillation, it works out where this capacitor is disconnected from this because this diode is reverse biased. So all it has is this little part here into C118. That's this capacitor. And why am I showing this side of the capacitor being tied to ground? Well, that's because of this PNP transistor here. When this voltage here is low, it turns this transistor on and it shorts this point to ground. This is the minus side of that C118, and so I'm showing it connected to ground. It's really to ground through that transistor. On the other half of the oscillation, this voltage is positive, which turns this transistor off, and it goes into a high impedance state where you could pretend like it's not even there. And that would be like this part of the circuit. So anyway, you now have this arrangement where now we're charging up C118. It's no longer in series with the load, it's now just being charged, and it charges up to about 6 volts. Meanwhile, this capacitor down here that we were formerly charging on this half cycle, it's simply connected to the plus 11 volt load. So it's kind of a charge pump, kind of a voltage doubler kind of arrangement. We're charging this capacitor up during half the cycle to 6 volts, and we're charging this one up, we're charging this one up, and then when we're connected during half the cycle, we actually put both capacitor voltages in series and thereby derive 11 volts from it. The other half of the cycle, we're busily charging the capacitors. So that's a simplification of what's going on, but I think it'll give you a general idea of how that works. Let's look at the input range selections. I've got both voltage and current functions represented on the same diagram. It's a fairly simple circuit, a lot of switches and not a whole lot else going on. The negative input terminal is always connected to circuit ground. If the meter is in DC volts or AC volts mode, in other words measuring voltage, the positive terminal is just connected over to the top side of this voltage divider. It's actually 4.42 meg, 4.42 meg, 470K in parallel with 1 meg, and that's your voltage cal for the whole meter. All voltages are calibrated by this single trim potentiometer. Assuming this is roughly in the middle of its rotation when you're precisely calibrated, which would be the normal design protocol. If you do the math and figure out the series parallel combination resistors, this works out to be 9.08 megs, so basically a big 9 meg resistor, followed by a 990K resistor, followed by a 10K resistor. The 10K plus the 990K is 1 meg. Add that to the 9 megs here, and you have the 10 meg input impedance. But there are only 2 tap points, here and here. And if you're in the 2 volt, well, if you're not in any of these ranges, this is the 2 volt switch, the 20 volt switch, 200 volt switch, and the 1000/750 switch, depending on whether you're in DC or AC. And you're not in battery test mode. So these are all the range switches right here. If you're not in any of those, then you have a ground potential that goes through all these switches. They're all shown in their normal position. If any of these switches is to the opposite position, then that's a depressed button. So these are all shown unpressed. So that ground is just rippling through all of these, and it's applied through some more switches to the input of the analog to digital converter. It just basically sees 0 volts. But if you engage, for example, the 2 volt range switch, now it's in this position, we're tapping off whatever voltage is on here, and then rippling that through all the other switches, and it makes its way to the analog to digital converter input. If you're in the 20 volt mode, if you've selected that, it does the same thing. It taps off the same point and runs through, so there is no difference here whether you're in the 2 volt mode or the 20 volt mode. It still taps off the same thing, so obviously that won't work if there is nothing else in the circuit to compensate for it. And in some of my other videos, you know that this is not unique to this model. This is a common technique. The more brute force approach is to have a big divider with more resistors, tap off between every resistor, so each range switch has its own tap position. That's the easiest, but a lot of meter designs use fewer resistors, and then they have the switching arranged so that you use the same tap point for 2 adjacent orders of magnitude. Again, for the case of the 2 volts or 20 volts, it's the same tap. Go down here, and this tap position is for 200 volts or the highest voltage range, 1000/750. So I mentioned earlier that the 7107, as it's being used in this particular meter circuit, has a sort of manual added on order of magnitude auto ranging function. It's not really auto ranging, it's manually selected by logic in the meter circuit, but it changes the sensitivity, the voltage sensitivity of the analog to digital converter, so it's expecting either a 0.2 volt maximum or a 2 volt maximum, and that's how it's able to compensate for not having as many taps. There's only 4 voltage ranges and only 2 taps, so whether or not the analog to digital converter is in the 0.2 mode or the 2 mode compensates for the fact that these 2 switches are doing the same thing with the same tap, and likewise down here. We also have the battery test switch. The battery voltage, which I mentioned in the power supply, it's really just reading right off the positive side of the battery. You have a simple voltage divider, and then that's fed into a filter circuit, and then that's fed in to here if the switch is in the battery test position, and that voltage then ripples through and goes to the input of the A to D converter. Now if you're in the current mode, now you're passing a current through this way. Well, it can't go directly like I'm showing it, of course, but it has to go through the meter circuit and then back out the minus terminal. So we'll continue up here, and if you're in the DC amps or AC amps modes or functions, then the current flows through here, through those switches, through the 3 amp fuse. This is only used when you're in the normal current mode, not the 10 amp mode. There's a pair of diodes facing opposite directions to circuit common, so they're basically across the input terminals but after the fuse. So basically if the voltage dropped across these shunts here exceeds the forward voltage of one of these diodes in either direction, one or the other of them will turn on, effectively shorting the input out, and the higher current will blow the fuse and thereby protect the meter. Here's the 2 milliamp switch. That's a range switch. The 20 milliamp range switch, 200 milliamp range switch, and 2000 milliamp range switch, which is really the 2 amp range. And you've got a shunt comprised of a 90 ohm, a 9 ohm, a 0.9 ohm, and a 0.1 ohm resistor. So the current flows through however many resistors are needed, depending on how much current you expect there to be. And again, depending on how much current is flowing through the shunt, you just do Ohm's law on it, and then you get a voltage drop that's proportional to the current. And that voltage is measured off the top of the resistor stack. And assuming you're not in the 10 amp mode, then the switch will be up here, and then that produces the voltage that comes back around through here, checks to see if it needs to go through the AC converter or not, and then continues on into the input of the analog to digital converter. So suffice it to say that if you're in the 20 milliamp range, for example, and you're passing 20 milliamps through this circuit and the switch is in the 20 milliamp position, that 20 milliamps will go this way through these 3 resistors. 0.1, 0.9, that's 1 ohm, added to 9, that's 10 ohms, and you can do the math with Ohm's law and determine that you're going to pick out a voltage up here, which will then get passed through all these, and that'll go into the analog to digital converter for display purposes. Now, what if you're in the 10 amp range? There's a separate jack for 10 amps. It has its own shunt resistor. It doesn't use these. And it's an order of magnitude below, so it's 0.01. And if voltage is dropped across that, and then that voltage is just run up here. And if you're in the 10 amp range on the meter switching, then that voltage drop again comes back around and goes into the analog to digital input. Now, as far as AC and DC switching, if you're in DC and you're coming out of the voltage part of the circuit, then you'll go through this switch and you'll go through this switch, and you'll just bypass the AC converter, and then again it'll come back around this way and go to the input of the analog to digital converter. But if you're in one of the AC switches, such as AC volts or AC amps, the AC volts would be routed this way and forced to go through the analog to, or the AC converter circuit. If you're coming in with a AC voltage drop across the current shunts, then that would run through here and go through the AC amp switch here and still make its way to the AC converter. And then depending if you're on AC volts or AC amps, the output of the AC converter is allowed to continue on into the input of the A to D converter. So that's the way all that happens. I also showed here part of the ohms switch, but I have a separate sketch for that. Now, I kind of stupidly arranged this sketch the wrong way. It should have been like that, but we'll have to live with it. I mentioned earlier when I was talking about the 7107 that just like the other chips in its class, it's actually a ratiometric measurement device. It's looking at the ratio of 2 different voltages, an input voltage and a reference voltage. And while normally you would hold the reference voltage constant and just vary the input voltage, in theory you could do it the other way around and hold the input constant and vary the reference. And that does get used that way in some meter circuits, but not in the 2260 meter. Anyway, you still have to have some voltage on the reference, and I chose to show it here on the ohms page. The reference high and reference low inputs, in this instance, the reference low is also tied to the COM pin of the 7107, and that is a voltage reference and gives it some relation to circuit ground. Again, I went into it more detail in my other videos where I explored the 7106, 7107 circuits in more detail, but the COM pin is internally regulated by the 7107 to be whatever its positive power voltage is for the chip, minus 2.8 volts. So in other words, in this case, it's a 3.2 volt above the circuit ground, but it's for this purpose we can think about it as being a 3.2 volt reference here, and therefore the reference low is at 3.2 volts. We have the regulated plus 6 volt power rail up here, and we have a couple of voltage dividers which return to circuit common. So really you can think about this being plus 6 volts up here and 3.2 volts at this point. So a voltage divider. This top resistor is actually only used during troubleshooting. Normally it's jumpered out, or jumpered out with a shunt on the circuit board. So you end up with a potentiometer, and it's in parallel with a fixed resistor, and then there's a span resistor on either side to limit the how much you can adjust it. And an identical circuit is here, although the resistor values are different. And this is the trim pot for the 0.2 volt calibration range, and this is the one for the 2 volt calibration range. The Heathkit schematic has a mistake in it. It calls both of them the 2 volt cal, but I determined that this one is actually the 0.2 volt cal. I mentioned before that the meter is counting on operating in two different sensitivities, one where 0.2 volts is the maximum input and the other where 2 volts is the maximum input. And here are two electronic switches. They're part of the same electronic switch IC that was talked about earlier. This one's controlled by the 0.2 volt control signal, this one's by the 2 volt signal. So depending on the ranges you're in and other things, circuit logic, one or the other of these could be closed and thereby establish the voltage off of one of these trim pots as the positive side of the reference voltage, while the minus side of the reference voltage is being held at 3.2 volts. So that's where the reference voltage comes when you're in voltage measuring mode. We already know from the previous discussion of the ranges that when we're in current mode, we're not playing that clever game of skipping every other order of magnitude. We actually have switches and shunt resistors for all orders of magnitude, but it's in the voltage range that we skip every other order of magnitude. That's when this 0.2 volt and 2 volt range become important. So in order to measure resistance, or ohms, this circuit uses one of several possible schemes, and in this case it's providing a constant current source that exits the meter on the plus terminal, flows through the resistor under test, and returns to circuit common or circuit ground. Because the current is constant, the voltage dropped across the resistor will be proportional to the resistance, and then the normal meter functionality that can measure voltages is brought into play to measure that voltage drop and display it. We can see here that we start out with a plus 6 volt power rail. We go through one of several different reference resistor paths depending on the range switch. We flow through this transistor here. It's a series pass transistor, through some protection diodes and a resistor here, through an ohms switch, out through the resistor under test and back to circuit common. And the voltage measured between here and here is tapped off through this and runs off to the input of the A to D converter. I should probably write on there that that's the A to D. And it's set up in such a way that for each range, the current that's held constant will be such that the dropped voltage will be within the range expected by the input to the A to D converter. Ignoring this top switch in the ohms range switch gang, this is actually the volts DC switch, or one of the gangs of that switch. We'll ignore that for the moment, and we just have the 2K, 20K, 200K, 2000K or 2 meg, and the 20 meg ranges. In each case there is one or more resistors that form a reference resistor. Sometimes it's just precision resistors, sometimes it's a precision resistor with a trim pot, and then that current, whichever path it takes to get through there, we know that current can't flow into or out of the input of an op-amp due to the very high impedance. So the current must go this way. It could flow through this transistor and on out as already described. Before we get into this anymore, we need to look at where this signal is coming from. Just like this circuit here, where we are picking off the reference voltage for the A to D converter, and again I am remiss by not writing that this is the A to D here. Anyway, so in the same manner that we're picking off the reference voltage by putting a resistor divider from the plus 6 volt power rail to the 3.2 volt reference, or 3.2 volt reference produced by the common terminal of the 7107, we have a similar divider here, comprised of this resistor, this one with a trim pot across it, that's the 2K cal trim pot, another resistor, and one that's shunted out during normal operation but can be unshunted for certain troubleshooting operations. If this trim pot is in its center, this ends up being about 5.5 volts measured from the COM terminal of the op-amp. Or actually from circuit ground, not from the COM terminal. So it's about 5.5 from the circuit ground. So with 5.5 volts there, that's brought around and it's brought into the negative input of this op-amp. There is no normal negative feedback on this op-amp, so it's operating as a comparator, which means it'll compare the two voltages on the plus and minus inputs, and whichever side is greater, the output will try to go fully positive or fully negative within its plus 6 volt or minus 6 volt power supply range. So let's look at what happens here. Let's just say that we're in the 2K mode. So this switch is closed. We've got these two resistors in series, and current would flow through there, but it's encountering a transistor which at the moment is turned off. So there is no current flow. There's no flow through this resistor. Therefore there's no voltage drop across the resistor, and therefore the plus 6 volt power rail is applied directly to the plus input of the op-amp. So with 6 volts here and 5.5 volts here, there's more voltage on the plus input than on the minus input. Therefore, the output of the op-amp tries to go fully positive. When it does, it forward biases the gate of this N-channel FET, and then that conducts, and then that causes Q102, this series pass bipolar transistor, it causes it to conduct. And now we do have a current flow through the transistor on out, through the resistor under test, and back to common. Now that we've got a current flow, now we have a voltage drop across these resistors. With a voltage drop here, that means this point can no longer be 6 volts. It's going to be 6 volts minus the voltage drop, so something less. If this voltage here is dropped enough that it's on the other side of 5.5 volts, now the minus input voltage is greater than the plus input, and being a comparator, this op-amp will flip in the other direction, drive its output fully negative, which will turn off the FET, which will turn off the series pass transistor and cut off the current flow. But in reality, this whole thing acts like a form of negative feedback, even though there's no direct negative feedback on the op-amp in the form of the usual short circuit or resistor. By way of this whole thing and the voltage drop derived here, it acts like negative feedback. So instead of this op-amp banging around between plus 6 volts and minus 6 volts at the output, it's actually going to sit at some voltage, whatever voltage is necessary, to result in a current flow that will cause the voltage drop to result in equal voltages at both the plus and minus inputs. So it's always trying to keep this point at 5.5 volts so that it matches this, and it will adjust its output as such until it gets that. Therefore, we now have a regulated or constant current flowing through that path. And as already mentioned, with a constant current going through the resistor under test, the voltage measured across it is directly proportional to the resistance, and it can be measured by the meter. All we have to do to measure a different range is select a different set of resistors, which will result in a different constant current being generated by this circuit. These diodes here are just to protect this circuitry if you do something dumb like hook up a voltage source out here. And this resistor here is inconsequential. It's also part of the protection, but it doesn't factor into the measured resistance, because all we're doing is looking at the current through here and the voltage developed across this, not across this. We could have quite a lot of different resistance values here, and they wouldn't affect this measurement at all. So what's with this volt DC switch up here and its relatively low value of resistor? Well, it turns out that when the meter is in the diode test mode, where you're trying to test the forward voltage drop or the voltage drop of a forward biased diode, there we go, the forward voltage drop of a forward biased diode, we need a different amount of current going through here, and therefore a different voltage. And so what is done is both the volts DC switch and the 2K ohm switch are closed at the same time, in addition to the meter being put in ohms mode. So now you have this resistor and these resistors effectively in parallel, resulting in a lower resistance than even this, and therefore the amount of current here is quite different from what it would be for normal resistance measurements. But that's what's necessary to result in a measurement of the forward voltage drop if you put a diode out here instead of a resistor under test. So that's why that's there. The only other thing I want to talk about in reference to the ohms circuitry is there are reference resistors, 4 of them, on the circuit board of the meter. A 1900 ohm resistor, a 19K resistor, a 190K, and a 1.8 meg resistor. These are actually measured by me to see what they are, and they're actually 1902, 19.07, 190.4K, and 1.801 megs. During calibration, these trim pots here, here, and here need to be adjusted for the 20K, 200K, and 2000K ranges. So those are all figured out by measuring across one of these resistors to this common point, and then adjusting the corresponding trim pot to get the reading that exactly matches these values down here. Now you may say, well, there's a range that's 1902, just a little bit less than 2000 ohms, and there is a 2000 ohm or 2 kilo ohm range, but it has no trim pot. Well, there's nothing directly to adjust there, but we still want to calibrate that range in general, and the way that's done is by the 2K cal pot, as I mentioned before. So the adjustment for that range is done up here by selecting the reference voltage of 5.5 volts, or approximately that, rather than having that fixed and adjusting up here. By doing so, we now have a constant 5.5 or thereabouts, whatever it needs to be to calibrate it. And then with that being fixed, then all the other ranges, the adjustments are made here. Now you may notice that for the 2 mega ohm range, it's using the same trim pot as the 2000K or 2 meg range, but it's got an extra resistor here, so it's running through less resistance than it would be in the 2000K range. So one trim pot does double duty to pick up the 20 meg range. You don't have a separate trim pot for that one. When I was talking about the input ranges for functions and range selections, I mentioned that when we're measuring AC volts or AC amps, the switching routes the scale, the signal, either from the resistance input voltage divider or the current function current shunts. Either way, the signal is routed through the switches, and if it's DC, it bypasses the AC converter, but if it's AC, it gets routed through the AC converter. So I want to talk about the AC converter briefly. This is a form of the classic precision op-amp rectifier, or op-amp precision rectifier. All of the Heathkits I've looked at so far, and some by competing companies, well, not competing, but companies like Fluke, use very, very similar topology on this part of the circuit. If they're not trying to do true RMS, this is just normal averaging precision rectifiers. This one uses a little bit more of an elaborate setup. As far as I can tell, the specs don't really justify it, but that's what they've done. I went and redrew this AC converter so that it's a little easier to make sense of the more conventional parts of it anyway. So again, you've got the AC coming in. Any DC component is theoretically blocked by this capacitor, and that's applied to the non-inverting input. And then we've got another DC blocking capacitor on the output here, so only AC signals can pass through there. And it's very conventional for there to be some sort of feedback mechanism, negative feedback mechanism on these circuits that applies only to the DC component or just DC feedback in general. And usually it's just a resistor tied from the output back to the negative input. There's something a little more elaborate being done here. I'm not really sure why. It's taking the output and running it through a voltage divider comprised of a 100K resistor and a 1 meg resistor, and that resistor is not going to ground, it's going to minus 6 volts, so the minus power rail. There's a stabilization capacitor on that junction, and then that voltage is what is fed back through a fairly high value resistor to the negative input. So this appears to accomplish in a more grandiose fashion what's usually accomplished by just a single resistor going like this. So then again we come out with our AC signal, we have the loading resistor, and I've drawn the two diodes in this fashion. So if it's a negative signal coming out of here, there's a path from the minus or the inverting input through the capacitor through this diode and back. So that's your AC negative feedback path for signals when they're below ground. Then if you've got signals that are positive or above ground, you go through this diode and now through a resistor and then back through the capacitor, and that's your negative feedback path for that half of the waveform. In that case, here we don't really have any restriction on gain other than what's accomplished by this capacitor and its impedance at the measured frequency. But in this half of the waveform, we have this value of resistor, and a 517 ohm AC calibration resistor. I've simplified it here. What's actually here is a 2K trim pot paralleled with a 698 ohm resistor. That makes it act like a 517 ohm resistor. And so you basically have a voltage divider here, and you tap off of that and run that back, and that's the voltage that's part of the feedback on the positive waveform. So that establishes the gain in that way. And you can adjust the gain by changing the value of this AC cal resistor. Now the other thing that made it confusing, besides the way this was, the way it is in actuality, being a pot and a parallel resistor, I'm getting bit by a tiny ant. I just stepped out into my garden briefly, and there was I upset a huge nest of little tiny bugger ants that just get all over you and bite you, and you can't seem to find them all. You just feel them later on. Anyway, this point here in reality is not tied to ground. It's a voltage divider from minus 6 volts to ground, but the values of the resistors are so skewed that the voltage you get here, while not quite 0 volts, it's actually minus 90 microvolts. I have no idea why they did that. It seems like at that point they could have just connected it to ground as I've shown it here in this slightly simplified version, but it makes sense this way. Let's see, we also have this other path that's factoring in here, and I don't understand why they've done this. They take the input signal and they run it through a 10 meg over 2.2 meg voltage divider and feed that through a capacitor back to this point. So what's that accomplishing exactly? I'm not sure. If I had the manual for the IM-2260, the Heathkit circuit description might shed some light on why they did that and why they did this down here. But in the absence of that, I'm just going to say, well, it's obviously something they put in there to tweak the performance of the circuit. Anyhow, at the end of the day, on the positive going part of the waveform, we tap off of the diode. It's already been compensated by the op amp for its forward voltage drop. So this is a half-wave rectified compensated signal, and that goes through this little RC filter because it's basically taking the average of this signal here, and then that's what's fed to the output of the AC converter, and then it goes on to the input of the analog to digital converter. So hopefully this version made a little more sense. Alright, well, I wasn't happy with the research I had done studying the 2260's circuitry regarding the so-called auto range that I discussed elsewhere in this video. In other words, where specifically in the voltage modes or the voltage functions, the resistor scaling divider only taps off every other order of magnitude, but the amps and the ohms modes do have resistive scaling for every order of magnitude. So it's necessary to tell the analog to digital converter to use two different sensitivities or two different input ranges depending upon which mode or which range is selected while in AC volts or DC volts. And I couldn't quite figure it out from what I'd sketched, so I did a more thorough job, and I've redrawn it here. It's a lot easier to follow. I won't go through the whole thing, but I also realized I hadn't covered how the decimal points are selected. The display has 3.5 digits, and there is actually, I think, 5 decimal points available, but only decimal points 2, 3, and 4. In other words, the ones in between the digits are used. There's no need to have one over here or over here. So the circuitry only drives those 3. And the LEDs are common anode, so the current flows in the common anode and then out through the cathodes for each segment. And that goes into the 7107, which sinks the current for whichever segment should be turned on. But for the decimal points, we have to sync the current separately from the 7107. So in each case, there's a 200 ohm resistor coming from decimal points 2, 3, and 4. And that'll make its way through some combination of switching to circuit ground. And that provides a current sync path to turn on the appropriate LED decimal point. As I had determined already, it was pretty clear that the 2 and 20 volt ranges have the same resistor divider node, and the 200 and 100 or 1000 volt ranges have the same resistor node. So there has to be something in the analog to digital converter that's looking for a 0.2 volt span or a 0.2 volt sensitivity, if you will. But when in 20 volt mode, since it's getting the same resistor divider, it's going to be going up to 2 volts. So the analog to digital converter has to be expecting 2 volts full scale instead of 0.2 volts. And then when we go to the next 2 ranges up here, the same thing has to happen. On the 200 volt range, it's going to be looking for a 0.2 volt input maximum or full scale. And on the so-called 1000 volt range, it's really in the 2 volt mode, although the meter is limited to 1000 volts. Although if you put 2000 volts on it, it would probably still read it, but it might damage the meter circuitry. And then there's also the battery range, and that also uses the 0.2 volt mode of the analog to digital converter. The same thing happens with AC volts, exactly the same things. In DC amps, as I already said, there's no need to auto range, so it's in 0.2 volt mode the whole time. Same thing for AC amps, same thing for ohms. But if we're in the diode test position, it does kick it into 2 volt mode. As for the decimal points, when we're in the lowest range of each function, decimal point 4 turns on. So for example, if we're in the 2 volt mode, the maximum voltage we can display is 1.999. So if we look at the display here and have 1999, the decimal point has to be here. That means decimal point 4 needs to be turned on. And this chart here shows that indeed, when we're in the 2 volt mode, decimal point 4 comes on. In the 20 volt mode, decimal point 3. In the 200 volt mode, decimal point 2. And in the 1000 volt range, there is no need for any decimal point, because then we'd be reading 1000, and there's no need for any decimal point. Same thing for AC volts. We can only go up to 750 in that case, and once again it would just be displayed 750 with no need for a decimal point. On ohms, it's also 432 and then nothing on the two highest ranges. I realized I made a small mistake here. I forgot that this switch here, besides being the battery switch, is also the 10 amp switch, range switch, and the 20 mega ohm range switch. So when I take that into account, I'd said before that in the highest two ranges of DC amps or AC amps, we did not have any decimal point on. In fact, in the 10 amp range of both, we have decimal point 3 on. And I did the math, and due to the shunt value, or the shunt resistor value that's exclusive to the 10 amp range, the display is going to develop a count of 1000, so you need to have a decimal point in the middle, and that is decimal point 3. And I verified it does come on the meter as well, so this table has now been corrected. And the same thing happens with ohms. When we're in the 20 meg range, decimal point 3 comes on. So that's the truth table, and it's verified. So I'm trying not to step on or repeat anything I covered in other video segments. But essentially these switches here, between them, determine which of the auto ranges we're in. In other words, is the A to D converter in the 0.2 volt mode or the 2 volt mode. They determine also which decimal point is on, and in addition they determine whether or not the display is blanked, because the common anode for all these digits comes through that point, or that 4 volt power supply circuit that I've discussed in the power supply section, and that has a blanking input on it that can reduce the LED supply voltage from 4 volts down to close to 0 volts whenever the blanking signal comes on. And the blanking signal does come out of these switches. Because when you're doing battery check, you're supposed to be in the DC volts function and the battery range, so obviously you want the display to be on. But if you accidentally had it in AC volts function while you're in battery check range, you'd get an invalid response, because the signal is being routed through the AC converter, and it's going to either show you nothing or some screwy low value. So the logic does detect that here in the switching, and it will turn on the blanking signal, which goes out to that 4 volt power supply and turns off the supply to the LEDs. So even though the A to D chip is trying to display some bogus value, the display will just turn off in that case, so you won't actually see the bogus value. So I want to make sure I didn't forget to cover this aspect of the auto range circuit. This little piece of circuitry here determines whether or not we have the meter in, or the analog to digital converter in the 0.2 volt range or mode, or the 2 volt mode. And it can only be in one of those at a given time, so it's one or the other. And this little piece of circuitry handles that. Out of all this switching, which is the same set of switching that handles the decimal points, it also does double duty as figuring out which of the two modes we should be in. And this signal here is the output of this bunch of switches. And when it's low, or 0 volts or ground potential, it puts the A to D in the 2 volt mode. If it's high, or plus 6 volts, then it puts the A to D in the 0.2 volt mode. So sometimes this set of switches actually pulls this signal high. For example, if you're in DC amps, then the switch is here and you actually just tie it to plus 6 volts. But in other combinations of switches, that isn't possible. So this resistor here is a pull-up to plus 6 volts, and sometimes this point just gets left hanging by these switches. It's not connected to plus 6 volts or to ground, and in that eventuality then this resistor makes sure it's pulled to plus 6 volts. And then that's applied to the base of this PNP transistor. The emitter is at plus 6 volts, and the collector has a resistor to minus 6 volts. So if this is low, then this transistor is turned on, and it conducts through here and develops voltage on this junction. And sure enough, that gives us a signal on the 2 volt mode control line. But if this is high over here, a high signal here would turn this PNP off, so it's not conducting. It's like it's not even there. And all we have is this pull down resistor to minus 6 volts. And that is applied to the control input of one of the electronic switches in the 4016 IC. The other switches in this IC are handling the rest of the range switching on the A to D converter. This resistor pulls this junction low. The low turns this switch here off, so it's not pulling this point low, and this resistor can pull it high, therefore this signal becomes high. So this is basically an inverter.